Welcome to the Bytecode. I'm your host Shafu, and today's episode is about Vyper, specifically about the modules in Vyper, which is a new feature. I'm really excited to take a look at that. And to walk us through it is Charles. Charles, thanks for taking the time, man. Okay, Charles. So yeah, it would be great if you can shortly introduce yourself and then walk us through the modules, how to use them in Vyper, and how they're implemented in the compiler. So yeah, Charles, it's your show.
Cool. Hey, I'm excited to be here. So I'm Charles. Big Tech Sucks on Twitter. I have been maintaining the maintaining the Vyper compiler for a few years now. And recently, this year, we released version 0.40 Vyper, which has a very important upgrade, which is a module system. Previously, Vyper didn't really have a module system, and part of that reason was because at the outset, way back in 2017, 2016, smart contracts were a lot simpler. And so there was this kind of guiding principle that contracts should be single file, which is like very auditable. But as, smart contracts have grown in complexity, it's become clear over the years that we do need a module system. And another reason it took so long is we wanted to make a module system that's really reasonable. I mean, by reasonable, I mean in the sense of like easy to reason about. And so the module system is very interesting for smart contract languages because we kind of have this concept of like a file as a contract, but we want to also be able to like import other contracts or files. When we're designing the module system, we wanted to like make it so that files look like contracts, but they can also be used as modules, like reusable code. There's kind of two aspects to that. One is like, okay, we have like stateless modules. So if a module doesn't have any state, like a file, it just has a bunch of like pure or helper functions. That's relatively easy to implement. There isn't a lot of design consideration there because you just kind of like import the files and then you like use the functions like in any other programming language, I guess. But once we get to like how to encapsulate state, things get a lot more interesting. And I think what you see in other smart contract languages like Solidity is, for example, inheritance. And what happens there is you kind of reuse code through inheritance. And one of the issues there is that it's kind of hard to see where state gets accessed. So if you inherit from A, B, and C, and then you touch some variable, call it X, you kind of need to know the entire inheritance tree in order to like know where X is defined, and then like also be able to find where it's touched. And in Vyper's module system, we wanted to make it auditable in the sense that like if you see a piece of state being touched, you can very quickly get an understanding, and ideally, even within the file, the single file that you're looking at, very easily get an understanding and context for what state it is, where it came from, and how it's used. So here I have the Vyper docs open, and I'll just walk through it real quickly. So we have a module which is a set of function definitions and variable declarations. And here's our first module. And this looks like a contract. And in fact, it is a contract. You can like deploy this. It won't do anything particularly interesting, but it is a valid, we'll call it a compilation target. So we've got this piece of state, we've got the owner, and then we have this pure function, which doesn't touch any state. And then we have this stateful function, which does touch the state of this contract. So let's see how this is used. So as we see in the docs, you can use this module's functionality just by importing it. So here we import it, and here's, various syntaxes for importing it. And as I mentioned above, this times2 doesn't touch any state. So it's really easy to use. And from the compiler's perspective, it's really also easy to design and implement. So we just import it, and then here we kind of use it. However, because this guy actually touches the state, the language design, the module design, prevents you from touching update owner until you're a little bit more explicit. So here is how you would actually use check owner. And what you need to do is, besides just importing it, use this thing called initializes. And initializes is a very important it's almost a keyword. It's technically not, but it's close. But we can think of it like a keyword. And this says that not only do we touch the state of ownable, we also initialize it. And what do we do in smart contracts when we initialize state? We actually have to allocate it. So this was a little detour. This is really another design issue that we ran into when designing it, which is that when you allocate storage, it's not just about the functionality of the contract, it's also about the storage layout. So this initializes statement is kind of actually it serves two purposes in the design. One is it tells you that you touch the state and you initialize it here, actually, meaning we call the constructor. But it also means that we declare where it is in storage. And so this allows the user to be very explicit. They don't need to rely on any initialization order or anything. When you see the initializes statement, that's where it is in storage. So if on the line above it, we had like foo is a uint 256, and then after we had like a bar is an address, all the state in the ownable contract would be allocated in the storage layout between those two variables.
Okay. So you're making the storage allocation explicitly with the initializers. Why isn't it a keyword?
We didn't want to overload the language too much, and also it's a little bit for legacy reasons. So we have this implements keyword. Let me search for it real quick.
Yeah, and another question would be, if your module doesn't initialize any state, you don't need to call initializers, right?
That's right.
Okay.
Sorry, we're failing at the search function. But for example, interfaces. So implements is this older keyword we have, which is not technically a keyword, but it has this colon in it instead. So yeah. Your question just now, if we don't import any state, do we need to initialize it? No, we can just use it because we can just call the function because it doesn't depend on any state. So it behaves kind of like a regular programming language, let's say. So in Python, you would just import the thing and then call the function.
If the module has 4 storage variables, it would just take 4 storage slots. Is that how it
Yeah,
works?
exactly. So you can think of it like this ownable thing is like an internal contract. So it's as if there's a little contract that is allocated. It's like a subcontract that's allocated wherever you have the initialize as statement.
Okay. How do you handle module in a module?
Yeah, that's a really interesting question. Basically, you only need to reason about it. One of the, design considerations is that you should only need to reason about it from the file that you're looking at. So here, ownable may have some internal imports, but we don't see any of them. So we just kind of use the functionality of ownable. But we'll get to that in a minute. So another thing is that we can actually, one thing I like about Python is that it's really monkey patchable. So there's no such thing as privacy. There's no private variables, there's no private functions or anything. You can actually modify anything in a module or class. And from the point of view of hygiene, it's not good to do that all the time. You can end up with some really messed up code. But in the case that you're using a library or somebody else's code that doesn't do exactly what you want, this can really save you because you can just actually modify something that the library designer didn't intend for you to modify, but it's actually needed. So here, you can just access any state in the module just by prefixing the variable with the module name, so ownable.owner. So I'm gonna skip this section and come back to it because you were asking about how we have modules within a module.
Yeah, Charles, one more question.
Sure.
If you could go back to the last, yeah. So there's no way to make a variable private in a module, so you cannot access it in the contract that uses the module.
Yes, that's right. This has been brought up a few times to me, but I think that it's kind of the way to go. In Python, there's this convention that if you, prefix something with an underscore, you shouldn't really use it. So it's kind of like private by convention, but if you really need to, you can touch it. Sorry, what's that? Right. By the way, you got a little quiet.
Yeah. I'm walking around in my room, and I'm using the mic of my MacBook. I just realized, so
Okay.
I'm not gonna walk away anymore.
Sorry, it's a little dry here because of the autumn.
All good, all good.
Right. So here we have initializes, and so I talked a little bit about the storage layout. Another thing is that if you have initializes, that must be paired with a call to init, except in the special case that it doesn't have an init function. But basically, you need to call the init function. And I'll get into the constraints around that a little bit later. Getting into nested modules. Sometimes you want to import a module, but you don't want to initialize it. And this is especially the case when you're designing a library. So let's say you want to import ownable, but you don't want to initialize it. You want to let the user initialize it. So what you do is we have this other special statement called uses. And uses means kind of what it sounds like. It means that you touch the state, either read or write, but you don't initialize it. And you also don't allocate it in the storage layout. So looking through this code here, basically we have a pending owner, which is something that we add. And in our constructor, we don't need to call ownable.init. We deal with our state. And then, but in these other functions in the module, we do use ownable's state. So we call ownable.checkOwner, but we're not initializing it.
Okay, I don't fully get this point. So what do you mean by it's not initialized? Isn't it initialized by default?
So if you try to compile this, the compiler will raise an error. I think you can think of this a little bit like an abstract contract, which means it has all these functions, but you can't actually instantiate it. And the reason you can't instantiate it is because ownable's constructor is not called. And part of this goes back to like the auditability. So we didn't need to have this uses thing. We could just like import ownable, and here we do like check owner or whatever, or like touch ownable.owner. But by having this uses statement, you can look at basically the header of this module, of this file, and know what state it touches. So you just like open up this ownable two-step, and you can see it uses this other module. And it also helps the compiler enforce some restrictions.
It makes it really explicit.
Yeah.
Which was good.
Yeah, and it's a little bit like some redundancy check or a checksum. So if you don't have this uses thing, then the compiler will complain when you get here, or when you get here. It'll say, excuse me, you're touching ownable's state, but you didn't say that's allowed in this contract. And the inspiration for this actually was kind of from, the Rust borrow checker. It's a lot less sophisticated than the borrow checker, but it's kind of similar in design or in spirit, which is that in Rust, almost the defining feature of the language is the borrow checker, and basically every time you instantiate a variable, you have to have an ownership. So you can think of this initializes statement as kind of ownership. So when you see initialize as ownable, you think, I own this module. That means I, allocate space for it in the storage layout, and I call its constructor. When you see this uses statement, you think, oh, this is like, I'm borrowing it. I'm not actually responsible for ensuring that it's instantiated, but I can touch the state. So it's kind of like so linear types in programming language theory is like this theory of things that are used exactly one time. And I think it might help to like go into an example to see how it's actually used.
Let's do it.
So here is an example where you import ownable two-step. And if you recall, ownable two-step has this stuff. It's got begin transfer, accept transfer, and it also has this uses ownable. So it lets the user instantiate ownable. So here, when we actually import ownable two-step, the compiler is going to complain unless we also initialize ownable. And that's really important because like just by looking at this contract, we know we can see where the dependencies get injected. So ownable has this state dependency on, ownable two-step has the state dependency on ownable, which we declare it here. And then here, we make sure that everything is initialized. So by the time we get to the end, this is an actual compilation target. So this file is actually something that you can instantiate and deploy. So we know by the time we get here that everything we need is instantiated. And we'll see some examples maybe where you could actually not initialize ownable and you could like still keep deferring its construction. So I don't know if you've seen some contracts where they have like these really deep constructors where you like inherit from X, which inherits from like base X, which inherits from like I, which inherits from base Y, which inherits from like base Y. And then you have to keep calling the constructor like all the way in and passing the, yeah, you have this like very nested constructor call. And by having this uses thing, this uses statement, which defers calling the constructor to some other contract, we actually can reduce that kind of nesting. We kind of flatten the nesting of the code.
Yeah. And this is a big feature of the module system Vyper, right? It shows that you can, when you use a contract, you can see every module that is initialized or where the state where you touch the state, you can instantly see that in that contract.
Yeah, exactly.
Okay, that's really cool.
Yeah. So like here, if we didn't initialize ownable, like if this was intended to be like another piece of a library, then you would see that. It would say uses ownable. Actually, in this case, I don't think we can because when we initialize ownable two-step, we need an initialized ownable. Or we need somebody else to initialize it, basically. And this is kind of the last part of the module system, which basically, and we'll get into more examples with snakebait and so on, but the other part of useful contracts or useful modules is obviously like being able to export functions. So in Vyper, we have this, goal of like being explicit. So if you import a module, that can never on its own put stuff into the selector table. It can never expose functions in a contract. So you need to do that explicitly. So like here, we actually have to like export these functions. And here's another example. And for convenience, there's also another syntax, which is you can export an entire interface, which is like a collection of functions, basically. But basically, the idea is in order to expose functions in your contract, you need to export them with the export statement.
Okay, so functions from a module are not exported by default. You have to do that explicitly.
Yes, exactly.
Okay.
So maybe I'll open a couple more examples, and then time permitting, we can go into the compiler code.
Sounds great.
Let's see if I can share a different window. Can you see this?
I can see your terminal here.
Okay, so this is kind of a contract that I have for kind of showing some of the ins and outs of the module system. So this is kind of more like a production contract. So it uses snakebait, so you can like import these modules, and then here is how in practice you would use them. So the snakebait implementation of base token, and by the way, you don't have to use the uses statement. You don't have to defer initialization to the user. It's kind of like the choice is left up to the library designer. So if you look at the source code for ERC20 in snakebait, it actually uses the ownable module. But it could just as easily do this, but that was just a design choice by snakemate because kind of I think Pascal, the author, kind of wanted the user to be really explicit and clear that they need to call the ownable constructor. So in the constructor, you have ownable.init. So as the user of the library, when you write that, you think, okay, I'm initializing the ownable module, and so I need to like keep track of the state. There's also stuff in here which isn't. Something was wrong with my syntax highlighting. Okay, there we go. Which isn't, the initialization isn't deferred. And that's just, the design choice of the library. because the library author was like, okay, we don't need the user to think about initializing the 712 domain separator, so we'll just do it for them. And so you'll actually see that in the init function, which is that the EIP 712 domain separator constructor is called. So here's just a couple more things that happen in this contract. Vyper feature with those structs, but it's not related here. So we export all the functions in base token. And then here is a couple examples of using the state that we've initialized. One kind of important aspect here is that, okay, so we touch base token.total supply. This is just some random function, you know. But it has to be qualified with the base token. Oops. So when you look at this line, you see that some state is being modified, but you kind of also instantly know where that state came from. You like, look, oh, okay, right? You know, we imported this module as base token, so we can go to the definition. So we don't have to like guess or like remember the entire import tree to find out where total supply came from or where it's touched. And similarly, we can call a function inside of base token. The compiler implementation of the module system will both of these count as touching state. You know, if you modify total supply directly, or you call mint, which itself should call touch total supply. So these both count as touching the module state. And here's just another example. Here's a utility function check owner, and here we see owner comes from this ownable module, which is right here, and we can open it up if we want. And it's got this owner variable, and the first thing we do in the constructor is transfer ownership. So some of the examples in the docs were kind of simplified from this code actually. So that's where the ownable two-step came from. So, but just going forward in the init function, so we have transfer ownership, and then it does all this stuff to, you know, the state, it sets owner to the new owner. And because we have self, we know that it's happening in this module. And then if we look at an example of how it's used, we can see ownable two-step. And this is exactly similar to what we had in the docs, which is we have this uses statement. So we use the ownable module. And that means we don't initialize it. We defer initialization to let the user initialize it. But, you know, we can still access the ownable module state. So we can call check owner, and then transfer ownership does something slightly different than ownable.transfer ownership, but it clears the pending owner, and then it calls the ownable transfer ownership. So I hope that gives you like an idea of the motivations for, you know, how the module system was designed, and kind of how it's used in practice, how it gives you code reuse, and also this idea of auditability, which in, you know, as you know, in smart contract land is very important.
Yeah, no, this is really cool. Like, to be honest with you, I never used Vyper because I really missed code reusability. So this is like a major thing for me. This is really cool to have now.
Yeah, I'm glad to hear it. And I hope it's as usable as we hoped it would be.
No, it looks really usable, and I love that you can infer which state is being touched just from looking at the contract itself. Especially for auditing and security stuff, it's like inheritance is a major pain point, obviously.
Yeah. Actually, one thing that is part of my personal style of programming is that I basically just use a text editor and grep. So, and I think it's kind of important for a code base to be greppable. Yeah, you do have tools, but sometimes they don't work or they break or you don't have them on a specific system. Or they have some assumptions that you don't have, I think is the main point. And being able to fall back to text to understand source code is really important. And so here, you can actually just like search the text and you can see that, yeah, okay, we have this uses statement, but we can also like find the 5 places in the code where ownable is touched.
This is really interesting, Charles. Like from okay, this was a big part of your design philosophy. Just give me a text editor, just give me Vim, and I want it to basically make sense for me.
Yeah, and I mean, I'm not saying that everybody should use Vim, and it's my personal, uh, style of programming that I've developed over years. But it's the idea that if you strive towards having a greppable code base, it'll also be clearer anyways.
No, that makes sense. Should we now jump into the compiler itself and see how it's implemented?
Sure. So yeah, that's it's a lot of code. Actually, this is one thing which is I didn't expect it to be as much code as it is, but it's a substantial portion of the front end now.
Hmm.
I would say
Interesting.
30% of the code, 30 to 40% of the code is kind of dealing with the uses and initialization system. A big part of that is tracking state accesses in the compiler. So like in order to implement this system correctly, we need to like track state accesses correctly. So that's kind of a refactor that that we did. That kind of benefits the compiler anyways because it's useful machinery to have, but it was new and it needs to be correct in order for the module system to be correct as well. So maybe I'll go in from the outside in. So here are the entry points. Well, the entry point is actually the parser, but let's skip to the AST. Here's where we have, initialize a statement, and this basically just is some validation to make sure that it's well formed. So you have like initializes some module or initializes some module with something inside it. And then here are like the checks that the AST is well formed. But yeah, that's just the syntax checking. And then we also have the uses statement, which is basically stuff like uses on. So the next step is how we actually look at this inside of the compiler. One sec. Is it okay if I take a restroom break?
Yeah, of course, man.
Hello?
Hey.
Okay, so we were at the AST. So we have these two statements types, initializes declaration and uses declaration. So the bulk of where the type checking happens is in this analysis folder. So we have all these helpers and files, but the main entry points are in this module.py, local.py, which analyzes functions, imports, which analyzes basically the import graph, and then global. And that analyzes compilation targets. So it makes sure that our uses and initializes statements are all well formed. So if we look at the order, actually, basically we do this thing where we parse it, which is up here. We resolve the imports, we analyze the module, and then finally, at the last step, we check if it's a valid compilation target. And basically that means that everything is initialized. I remember in the example in the docs, there's like these kind of somewhat similar to abstract contracts. You can have files which are valid modules but can't be compilation targets. But if we're at the stage where we're trying to like compile a contract, we need to check that it's a valid compilation target. So the meat and potatoes here is in this uses declaration. And the initialize declaration. Basically, what we do here is we kind of reify everything. All this is, it ends up just being kind of like a graph search. So the uses declaration is fairly easy to analyze. You just like go through these declarations and set the ownership that we have over that imported module. And then whenever we see an initializes declaration, we need to kind of recurse into all of the modules that are used by that module and make sure that they're initialized. So after we have gone through and reified everything and set ownership, so that's like at the top level of the contract, sorry, of the module. So we have like import initializes foobar, and then we have like uses QUX or something. But like this on its own is not a very interesting contract, right? Like usually an interesting contract has functions, my function, and then, you know, foobar, do something. So the next thing we need to do after we've kind of like gone through and recorded all of the things that are initialized or used in this module is like, we actually need to analyze the functions. And so we kind of go into the function and analyze it. And basically on every statement or expression in this function, we're going to check that it's like, or we're going to log which actual pieces of state it uses. Sorry, you said to get as technical as I want, so we're really going into
Yeah,
really how
let's
it
do
works.
it. Let's do it.
So everywhere we see any expression that uses state, then we need to like log that module is used. So we call this thing mark used module, and what happens there is, you know, so this is like a set of modules that my function uses. So like if we have like my function, and then it does like foobar, more familiarly, ownable.owner equals, I don't know, empty address, then this function, then some other thing, some module.foo equals 5. So when we analyze this, eventually we're going to have a result, which is that you can think of it as like my function uses ownable and some module. And that's like the summary that we really are interested in. And yeah, like I said, that happens here. And there's basically a couple places that can happen in the actual language, but this is handled here in a very general way. So we just like, anytime we see a state variable that's read or written or a call, to a module, we kind of log, or sorry, collect, I guess, all the things that it reads and writes. Okay, so yeah, so just to break it down a little bit more. So we have like def my function, then we have like my module dot foobar, and here we basically log writes. And here we kind of recurse into foobar and, you know, reads, writes, whatever foobar reads, writes. And then at the end, we finally have this nice summary, which is the used modules that we saw in the function type. So we just to recap, we looked at the top level of the module, we found the uses and initializes statements. And then now we went through the code of the function and actually found what pieces of state actually reads and writes. And then at the end, we're going to call this validate compilation target. And this is a global constraint. If you think about the import graph, that's something that you can only prove once you have a contract that you're intending to compile. You recurse into all the imported modules and all the initialized and used modules, and then you prove that it's correct. So this is basically the definition of how the algorithm works. You go through, you collect all the used modules, you collect all the initialized modules, and all of these things are just kind of the recursive thing you want. By the way, part of the reason this takes more, it's a little bit verbose, is because we spent a lot of time being able to construct proper error messages. So we could do this in kind of like an abstract way, which is we just like prove properties about the graph. But actually what we're doing here is we're actually like also collecting AST nodes while as we're going along. This way you can have good error messages. Just check that this compiles. So if we like actually initialize this twice, we're gonna get some relatively nice error message. And that's not exactly the error message that we were looking at in the code, but yeah, the point is that there's some amount of effort here to like make sure that the error messages are good. So like if there is an error, like the contract doesn't validate, the compilation target doesn't validate, then we can tell the user why. Like here, we say like add this initializes thing to your contract. So after we've done all that, this basically says everything that we've used, make sure it's initialized. And here we have the other side of the constraint, which is like if something is initialized more than once, then we raise an exception. And I can actually get us to import my module. So here we've violated the constraint, right? So my module initializes ownable, but my token has also initialized ownable. So what happens? I see. So what I've done here is kind of interesting, which is that I've imported my module, but I haven't initialized it. So the compiler is treating it as a pure module. We haven't actually used any of the state. We don't care that it has its own initialized modules because we're not allowed to touch it, so it doesn't care. So if we have initializes my module, and hopefully we don't find a bug here. Okay, so now it's telling me we need to call like my module dot init. Okay. my module dot. And now we see what happened. We violated the initialization constraint because this guy initializes it and this guy also initializes it. So we could fix it by demoting this from initializes ownable to like uses ownable and see what happens. So what happened here is, right, we like called the init function, but we didn't say we're initializing ownable, so that's an error. So we comment that out, and that works. So what I just did is basically, instead of initializing ownable, I've deferred initialization into somewhere else in the import graph. And one thing that you'll notice is like, it doesn't matter where in the import graph. Like, even though base token knows nothing about my module, like the import graph is something like self, it imports my module, which imports ownable, and we import ERC20 base token, which also imports ownable. And then we also import ownable. So the constraint system doesn't actually care that ERC20 doesn't know anything about my module, right? So we have my module, and my module is not a parent, it's not a child of ERC20, it just exists somewhere else in the import graph. But so long as we have this constraint satisfied, which is that everything that's used is initialized exactly one time, the constraint system is happy. So here we have uses ownable in base token, which we saw before, which I'll pull up again. But that also just initializes ownable here. And then in my module, we initialize ownable. So the important thing is that that constraint is satisfied. So we have my module is initialized, and then my module initializes ownable. So everything is copacetic now.
Nice. Well, Charles, this was, yeah, really cool to look. I never looked at the Vyper compiler before, to be honest with you. Obviously, using Python makes it a lot more readable than, for example, the Solidity compiler. Yeah, I think that was a big missing piece to Vyper for a lot of people. So it's great to have that now. What does the future of Vyper look like? Like what do you want to improve or add to the language?
Yeah, that's a really good question. So there's a lot of things we're working on, not just with the language, but also with tooling, education. So some non-language things that I'm really excited about are, Cypher Updraft has recently released this Vyper course, which should make it a lot more approachable for like newcomers. And then also, we're trying to increase our presence at more conferences and on social media so that people are like more aware of, all the recent developments with Vyper. In the language, there's a few things that we're working on that are important and I'm excited about. One of them is there's some efficiency things. So we're like adding struct packing and storage, which is highly requested. We're working on this new backend for Vyper. It's a new intermediate representation. It's called Venom, and maybe I can go into that on another episode or something because it's very interesting and we're able to produce really efficient bytecode now. And then there's some more things in the... Another thing about Venom is that, we want it to be kind of like LLVM, but for smart contracts. So you kind of target the Venom intermediate representation, and then you're able to have multiple front ends compiled to that, and then also target multiple back ends. And then some other things that I'm working on in the front end are like some kind of like abstract functions, so you can kind of defer implementation of specific functionality to like a user of your library, for example. And also things that we're thinking about are like traits or like generics, and generally making like the language more powerful.
Interesting. Yeah, I've never been so excited about Vyper as I'm right now. I think it's in a great spot. Yeah, as I've said before, like for me personally, the big missing piece was modules. I never wrote much inline assembly, for example, so I didn't care for that too much, but modules was a big thing for me. So yeah, really excited to have that in the language now. So yeah, Charles, thank you very much for this walkthrough. Yeah, let's try to do a part. I would love to look at Venom, somewhere in the future, maybe in a couple of weeks or so. But yeah, thank you very very much for this walkthrough.
Yeah. Yeah, thanks for having me. This has been really fun.
Awesome, guys. Thanks for tuning in. I will put the GitHub and the Viper docs down in the description below. And yeah, thanks for tuning in, and we'll see you in the next episode. Bye
Thanks so
bye.
much, Shafu.
Bye bye.
See you.